graphing relationships. So we're going to look at different relationships and the way that they are going to present themselves. So for your homework, we talked about the difference of the speed of the car. If it's going up, it was getting faster. If it was going down, it was getting slower. If it was staying flat, it was staying at a constant speed. So today, we're going to make sure that we can match simple graphs to situations, similar to what you guys did in your homework. So if that seemed easy, then you should be okay there. We're going to graph relationships, and then we're going to describe relationships as increasing, decreasing, or constant. Okay, so we want to state whether each word or phrase represents the amount that is increasing, decreasing, or constant. So if I say the word stay the same, does that mean I'm increasing, decreasing, or constant? Constant. Perfect. If I say the word rises, increasing. Drops would be a decrease. And slows down would still be a decrease. Good. Okay, so we can take words from our English language and decide whether we think it would be a graph that's constant. And remember, a graph that's constant is flat. A graph that's rising or increasing is going up. Decreasing is going down, left to right. Decreasing, going down, left to right. Okay, so graphs can be used to illustrate many different situations. For example, trends shown on a cardiograph can help the doctor see how a patient's heart is functioning. To relate a graph to a given situation, we can use keywords in the description. So here you have some examples. Notice what's on your x-axis of this cardiograph. It is what?
Seconds.
Time, right? So as time's going on, what's happening to your ICG? It's fluctuating up and down, right? It's going up, down, up and down, up and down, up and down. So it's kind of cyclical, right? In here, huh? Someone asked what? Huh? Well, I think it's panel C and panel A, so it's two different people probably with their ICG. Yeah, they look the same thing. So it's just isolating. It's going back and forth. It's fluctuating up and down. All right, so let's make it a little bit easier than crazy graphs like that. So in example 1, we have a situation where we have leaves falling from a tree. Okay, so everybody can envision leaves falling from a tree, right? One day, a gust of wind blows off many leaves. Eventually, there are no more leaves on the tree. Which graph do we think would represent this situation? Notice that my x-axis is time. So as time's going on, what's happening to my amount of leaves?
It's decreasing.
Why can I eliminate A? This means my leaves increase. All of a sudden, they're magically reappearing on the tree, and then they're staying there, and then they drop. So it can't be A, so we're going to eliminate A, because that's no good.
I said B.
So now we're going to look at B and C. So B and C, they both are dropping off. We're not increasing or staying the same. So now, if they are falling from a tree, and then one day a gust of wind blows off many leaves, would that be a steeper or a less steep drop? It would be a steeper. So here we kind of have like a constant, and then it stays the same, and then it drops. So I'm thinking B, right?
Yeah.
So we have some leaves dropping. Here is my gust of wind, right? My gust of wind is kind of happening right here in this section. And then eventually more leaves fall off until there are no leaves left on the tree. Okay, so B, I agree with that one. Circle it. All right, so now let's fill in the table based on the above example. So what would it look like on an actual graph? So each day, several leaves fall, which means it's never going to be horizontal. So what would that look like as a graph? It would just be going down from left to right. If wind blows off many trees, then it's going to make it steeper. So make sure your slope down is steeper than the one that you had above. And then eventually it's going to have none, which means it's going to hit 0, right, on our x-axis. So if we think about this as being our x-axis, eventually it's going to hit at 0 because there would be none. So we put all that together. It created the graph from up above. Good? All right, example 2. The air temperature increased steadily for several hours, then remained constant. At the end of the day, the temperature increased slightly before dropping sharply. Choose the graph that best represents this situation. Let's fill in the table first this time before we make our decision. So if we're increasing steadily, what would that look like? A slight increase. So we're going to be going like up. Oops, I should not do that in yellow. Can't see that. So going up. And then when we remain constant, it's going to flatten out and go horizontal. And then increase slightly before dropping would look like what? Another, so we're increasing slightly and then all of a sudden it would drop shortly.
No, it's like an upside down check mark.
Right? So if we put this all together, which graph up there seems to be the match? So we're going up, constant, another increase, and then drop. So if I look up here, it looks like C has that, right? So up, constant, up more, then drop. Here we are constant first in A, and then increasing, and then dropping, and then constant. In B, we're constant for a little bit. We've got an increase, then constant, and then a quick drop. So yes, I agree. C, circle it, is our best choice. Okay, is everybody good? All right, so as seen in example 1, some graphs are connected lines or curves, which we call continuous. Oops, I'm in highlighter mode. Continuous. Because if I were to draw out the graph, I'm not picking up my pencil tip, right? It's continuous. It's continuous the whole entire time. I don't have to pick it up. Some graphs are only distinct points, and these would be called discrete. Oops, I think that should be an I. Discrete graphs. So discrete graphs would be just points instead of a continuous. So for example, if I wanted to graph people versus time, we don't have 2.67 of a person, right? So I can't have a continuous graph reflecting people. I would have 1, 2, 3, 4, 5, and so forth. So that would be a discrete graph versus continuous. Hayden, third time I'm saying your name. All right, so now here we have the graph on a theme park attendance is an example of a discrete graph. It consists of distinct points because each year is distinct, and people are counted in whole numbers only. The values between whole numbers are not included since they have no meaning for the situation. So here we have attendance, our years, and how many people. So if I had to come up with a story about this graph, what would you say?
People.
What's happening to attendance of the theme park as the years are going on? It's decreasing, right? We're getting less people coming to the amusement park as the years go. It was just looking at it as an example. This is an example of what a discrete graph would look like. Discrete. These are examples of continuous graphs because they're continuous. I'm not picking up my pencil tip as I graph it, okay?
Like points.
Yes. Okay. All right, so now let's go ahead and sketch graphs. We're doing the opposite. So sketch a graph for this situation. Hayden, move, please, to this group. Sketch a graph for the situation. Tell whether the graph is continuous or discrete. We have a truck driver enters a street, drives a constant speed, stops at a light, and then continues. So first, let's decide, are we going to be discrete or continuous? It's about the truck driver driving. Continuous, because we don't do 1 mile per hour and then all of a sudden jump to 2 miles per hour, right? We continuously flow our speed. It's not just whole numbers. Okay, so it's going to be continuous. So now we have to figure out what's happening. We've got enters a street, drives a constant speed. So if he's entering the street, that means he's probably starting at what speed?
A little bit.
0.
Probably starting at 0, and then we're entering the street, right? And then he drives at a constant speed. So when he enters the street, what would be happening to my speed? From 0, it would increase a little bit, right? And then we go constant for a little bit. So that means I'm going to do what?
Constant.
Line.
Straight line, okay. And then he stops at a light. So now what's going to happen to my speed?
It's gonna completely just drop down.
It's going to decrease down to 0.
Decreasing. Never mind. I forgot.
And then when we stop at a red light, what happens?
Wait.
We stop for a little bit. So we have a flat line on our x-axis. And then now it turned green. What's happening? He's going to go back up to speed, right? And then are we going to keep on accelerating, or what's going to probably eventually happen? It probably goes back to constant, right? Ran out of space on my x-axis. Has everybody got that? Okay. So we said that this graph would be continuous. All right, example 2. Let's see if we can tell the story here. A small bookstore sold between 5 and 8 books on each day for 7 days. Oh, so here they already gave us the graph. That was nice. So on day 1, they said they sold 5 books. On day 2, they sold 5 books. Day 3, they sold 6. Day 4, they sold 7. Day 5, they sold 7. Day 6, they sold 6. Day 7, they sold 7. So is that continuous or discrete? Discrete. Good. Beautiful. All right, so now, easy peasy. That's it for your notes. So now what I want you to do in your group is work through these guided practice problems, please. Is that on there, the guided practice? Yeah? So you got 1, 2, 3, 4 problems I want you to work on with the people around you. Go.